In this lesson, we will discuss limit laws, which are several easy rules used to calculate limits of functions that are combinations of functions that have known limits. So to set our groundwork for our limit laws, let capital L, capital M, C, and K be real numbers, and we're going to assume that we know that the limit of the function f as x approaches c equals L, and the limit of g of x as x approaches c is capital M. So recall what this means. This means that as x gets closer and closer to c, the values of the function f get closer and closer to the number L, and the values of the function g are getting closer and closer to M. Then the first limit law is called the sum rule, and this says if you take the limit of f of x plus g of x as x approaches c, then the answer will be L plus M. So in other words, the limit of a sum of functions equals the sum of the limits. The second limit law is similar. It's the difference rule. This says if you take the limit of f minus g, limit of f of x minus g of x as x approaches c, then the limiting value of this combination will be L minus M. Remember, f is getting closer to L, g is getting closer to M, so f minus g will be getting closer and closer to L minus M. The next limit law is called the constant multiple rule. If you multiply the function f, or any function, by a constant k, so k is just a number, a real number, then the value of the function f is still approaching capital L as x goes to c. So k times f of x will approach k times L. In other words, the limit of k times f of x as x approaches c should equal k times L. When you multiply two functions, we get the product rule. If you're looking at the limit of f of x times g of x as x approaches c, you would get L times M. And similarly, the quotient rule tells us that the limit as x approaches c of f of x divided by g of x will equal L divided by M, but you have to watch out in case M is 0. You can't use the quotient rule. There's other techniques that you could use. But if M does not equal 0, then the limit of f divided by g will equal L divided by M. The sixth limit law is called the power rule. If you have the function f raised to the power n, where n is a positive integer, and you take the limit as x approaches c, then you will get L to the power n. Now this is just a consequence of the product rule, where all the factors of the product are f of x. So the limit of f of x to the power n as x approaches c equals L to the power n. The last limit law we're going to look at is called the root rule. If you're taking nth root of a function f of x, and you want to look at the limit as x approaches c, then you can obtain this limit using this rule, the root rule. You will just get the nth root of L, assuming that n is a positive integer. If we're taking an even root, like a square root or a fourth root, we're assuming that the limit L will be positive. So we're not taking any even roots of negative powers. So these are called the limit laws, and so we'll look at some examples of how we can use limit laws to evaluate limits. There will be easier techniques to evaluate limits, but these are the foundational rules that we will build much easier techniques from. And these are also the rules that will help us later in this class when we discuss things like derivatives of functions and the different rules for taking derivatives of a function. So the limit laws are kind of the foundational tools which help us evaluate limits. Now let's look at some examples of computing limits using the limit laws. Let's evaluate the limit of 2x squared minus 3x plus 4 as x approaches 5. Well, this is a polynomial, and so we can break up the three terms of this polynomial using the sum and difference rules. So by the sum and difference rules, I can write this as the limit of 2x squared minus the limit of 3x plus the limit of 4, all as x approaches 5. Then by using the power rule and the constant multiple rule, I can write the limit of 2x squared as x approaches 5 as 2 times 5 to the power 2. I can write the minus the limit of 3x as x approaches 5 as minus 3 times 5, and the limit of 4 as x approaches 5 is 4. Now we can simply put this together and evaluate to obtain 2 times 5 squared, which is 2 times 25, or 50, minus 15 plus 4, so this equals 39. So the function 2x squared minus 3x plus 4 will be getting closer and closer to the value 39 as x gets closer and closer to the number 5. So we say the limit of 2x squared minus 3x plus 4 as x approaches 5 is 39. Now let's evaluate the limit of the function x cubed plus 2x squared minus 1 all over 5 minus 3x as x approaches negative 2. I'm first going to use the quotient rule to break this up as the limit of the numerator divided by the limit of the denominator. So by the sum and difference rules, we obtain this expression. And then finally, I'm going to use the power and product rules again, so I can replace all the x's with negative 2 to obtain this expression. And when we evaluate the numerator, we'll get negative 1, and the denominator simplifies to 11. So the final answer is negative 1 over 11. So the limit of x cubed plus 2x squared minus 1 over 5 minus 3x as x approaches negative 2 is negative 1/11. Let's review the previous two examples. The first example we saw using limit laws was that the limit of 2x squared minus 3x plus 4 as x approaches 5 is 39. And we use the limit laws to break this up. But if you notice that the function in parentheses is a polynomial function. So if I defined the polynomial function p of x to equal 2x squared minus 3x plus 4, then notice that p of 5 is 39. So we see that for a polynomial function, to evaluate the limit of a polynomial function, all we have to do is plug in the limiting value of x, which in this case is 5, into the function. This also works for rational expressions as long as you're not dividing by 0. We saw that the limit of this rational function, which is a fraction of two polynomials, the limit of this rational function, it was negative 1 over 11. But this is what you would obtain simply by plugging in negative 2 for x into this expression. So this just equals r of negative 2, where r of x is the rational function x cubed plus 2x squared minus 1 over 5 minus 3x. So as a consequence of the limit laws, we can evaluate limits of polynomials and rational functions very easily. This is a technique called direct substitution. So we can simply plug in the limiting value of x into the function and we can evaluate the limit. So direct substitution works for polynomials and rational expressions. So if I have two polynomials, p of x and q of x, then the limit of p of x as x approaches a equals p of a. So I can evaluate this limit just by plugging in a into the function p of x. And the limit of the rational function p of x divided by q of x as x approaches a will just equal p of a divided by q of a. And this works as long as you're not dividing by 0. In other words, if q of a does not equal 0. So let's see an example of direct substitution. If I want to evaluate the limit of this rational expression, I notice that by plugging in 1 in the denominator for x will not give me 0, so I can use direct substitution here, and so this limit will just equal 1 cubed plus 4 times 1 squared minus 3 divided by 1 squared plus 5. This simplifies to 2 over 6, which further simplifies to 1/3. So by direct substitution, we don't have to evaluate this limit using every single limit law that was possible. We can now just use this consequence of the limit laws called direct substitution to evaluate this limit. This next example will use the root rule for evaluating limits. Here we have the limit of the square root of 4x squared minus 7 as x approaches 2. By the root rule, I can evaluate this by taking the square root of the limit of 4x squared minus 7 as x approaches 2. And inside this radical, we have a polynomial. So by direct substitution, I can evaluate the limit inside the radical as 4 times 2 squared minus 7, which simplifies to the square root of 16 minus 7, or the square root of 9, which equals 3.